Okay, so here's our general setup. Daily summary, just tell you what we're going to learn about today. There'll be a demo, hopefully less than 15 minutes, and then a chance for you to work on those concepts in your groups. All right, so today we're going to review and extend our knowledge of sets and set notation and start learning about how to write proofs. All right, a set is a well-defined collection of things, elements, or numbers. Just a collection of things. And the term well-defined means there's no ambiguity as to whether or not an object belongs to a set, right? Either it does or it doesn't, and you can always tell. So that's what well-defined means. A set can be finite or infinite, have a finite number of elements, or it can have an infinite number of elements in it. Some common sets of numbers include the integers, which we represent with a capital Z. Some texts will represent it with the Z with an extra line, which is what our text does, and some will just bold the Z. So you can kind of do whichever. Q represents the set of all rational numbers. R represents the set of all real numbers, and C is the set of complex numbers. There are several ways to describe the elements of a set. 3 common ways are listed here. We could describe it in words, just describe the elements of the set in words. You could make a list of all the elements in the set. That's called the roster method. And you always put them in curly braces when you list them. Note that the order that you list the elements doesn't matter. And you could use set builder notation, which generally looks like this. There's a curly bracket, and you would read this as the set of all x's such that, the vertical line is read such that, x fulfills some condition. So the symbol that looks kind of like a weird looking E means is an element of. So E that can stand for element. So it means is an element of. So for example, I could say 8 is an element of the integers, right? 8 is an element of Z because Z stands for the integers. So let's talk about the rational numbers. I want to describe the rational numbers using all 3 methods, words, roster, and set builder. Even though we can shorthand abbreviate it as Q, just as an exercise in doing this the 3 ways. So how would you describe the rational numbers in words? What are rational numbers? Numbers whose decimal expansions don't go on forever. Yeah. That is an attribute of rational numbers. But is it the definition? The root of the word rational is a ratio. Go ahead, Tim. Yes. Numbers that can be expressed as a ratio or a quotient of integers. Any number that you can write like as a fraction, where you have an integer on top and an integer on the bottom. Is irrational. Yep. I is an imaginary number. It would not be considered rational. Yeah. Because, yeah. No, the rationals are a distinct set from the non-reals. Yeah.
Well, I'm not saying that the rationals. Do you have an irrational number?
Sure, you could have an imaginary number who's like, yeah, like pi I, something like that. Yeah. Yeah. All right. So can I what? No. Well, Like root 2 plus 1?
Well,
2e would be irrational. Yeah. So 2 is a rational number, and then e is irrational, right? The product of them would be irrational. That's kind of the thing we're going to talk about. Sure, 2 is an integer. Yep. Yep. All right, if I wanted to make a roster, a list of all the rational numbers, all the numbers that you can write as a fraction where the top and bottom are both integers. This is a little tough. So I could try to be, sort of smart about how I make the list, and I could say, okay, let's write out all the numbers, all the fractions that have a 1 on top. Right, so I could do like 1 over 1, 1 over 2, 1 over 3, 1 over 4, and I could just keep doing that, right? No, because Z represents a whole set. So you're moving into set builder notation. Yeah, you could definitely, that's what we're gonna do when we write it in set builder notation. We're gonna say an integer over an integer and use symbols to represent that. But if I'm trying to write it out in roster form, where you list every one, that's hard, right? That's sort of the reason we invent set builder notation. So I've got, these are all the fractions, all the rationals that have a 1 on top. And then I could try to write all the rationals that have a 2 on top. 2 over 1, 2 over 2, 2 over 3, 2 over 4. I'm going to get a little bit of repeats, right? Like I have a half here and I have 2 over 4 here. I'll have some repeats, but I don't think I'm going to leave anything out if I do this correctly. So then I could do 3 on top. And then I just keep doing that forever, right? Then I could do 4, numerators of 4, numerators of 5. That's a pain to write in roster notation. So that's sort of why we say set builder. So what Todd was just suggesting is like, can't we just say an integer over an integer, right? So we could say the rationals are the set of all fractions, a over b, such that a and b are both elements of the integers. So the set of all fractions where the top and the bottom are integers, and I need one more restriction. What do I have to say? Yeah, b can't be 0. Oh yeah, that little comma you can read as b, a and b. I could also use the little caret symbol for and, whichever one you like. Yep.
so the set of sets.
The set of sets is a set, yes. Uh-huh.
That's kind of a composite category.
Yeah.
Like if you think about it as a two rational, then you realize it's still two of something.
Yeah.
But that's something.
But that something is irrational. Okay,
You
yeah.
find those in any number of ways, as long as that is rational. You can't reduce set of 4.
Okay. The empty set, sometimes also called the null set, is just a set with nothing in it. You can denote it with a set of brackets with nothing between them, or as a 0 with a line through it, but not both. Right? So if I said the set of days of the week that don't end in y, yeah. Are there any days of the week that don't end in y? That is the empty set. So you would just say, oh, there's nothing in that set that you're talking about. So one way to describe two-dimensional space is the coordinate plane, right? The XY plane, we use it all the time. It's often referred to as R2, right? the real numbers in 2 dimensions. You've got an x dimension and a y dimension. Each of those lines is a real number line. Every point in the coordinate plane is given a set of coordinates, x comma y. In this course, we often use a vector to express the coordinates vertically, x, y, instead of horizontally, x comma y. They mean the same thing. So if I want to describe R2 using set builder notation and this new vertical vector notation, I would say R2, that set is the set of all vectors x, y, such that x and y are elements of the real numbers. So that describes the entire xy plane. Set of all ordered pairs x, y, so that x and y are both real numbers. That make sense? Okay. All right, so I want to take a quick look at the writing proofs handout together. Some page, I don't have them numbered, sorry. A couple pages later. Writing proofs. How do we put what together? You don't get this notation?
No, I don't get how that
Represents the coordinate plane.
Yeah.
Okay, so alternatively, I could have written this as all ordered pairs x, y, right? Such that x and y are elements of the real numbers.
So vectors are always
A vector is just a list of numbers. It's just a list of numbers written vertically. So it's just a new notation that we are going to use as an alternative notation to a point x comma y. You write it vertically x, y. Okay, so writing proofs. Spend a couple minutes on this. This is going to come up multiple times throughout the semester. Today is the first time we're going to talk about it. A proof is an argument designed to convince someone that a statement is true. Writing a proof is similar to writing a piece of music. The process is both creative and logical. There are rules and customs that you must follow, right? But there is no routine or procedure that you can use to write a proof or a piece of music. There is no, this is the way. Just follow this procedure and you'll have a song, right? You can't do that. It's the same with a proof. Okay, so writing proofs is a skill, a knack that you develop over time with patience and practice. There are a multitude of types of proofs, but the vast majority of proofs can be proven, the vast majority of statements or theorems can be proven with one of 3 types: direct proof, proof by contradiction, and proof by induction. Today we're just going to talk about direct proofs. Most theorems can be written in the form if something, then something else, right? So you could read this: if triangle, then square. But triangle and square are themselves statements, that is, things that are either true or false. So the statement triangle is called the hypothesis of the theorem, and the statement square is called the conclusion of the theorem. In a direct proof, you assume that the hypothesis triangle, the hypothesis is true, then give an argument that convinces all readers that square, the conclusion, has to be true. So it would sound something like this: we assume triangle is true, therefore such and such is true, which means that something else is true, so square must be true and the proof is complete. So in a direct proof, you assume triangle is true, argue, 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 conclude square must be true. So our first goal is going to be to prove that the sum of two integers is even. So first, write the statement in if-then form. If n and m are even integers, then n plus m is even. Then we assume the hypothesis is true, that m and n are even integers. Okay, assume that n and m are even, and then we construct an argument which shows that the conclusion, n plus m is even, must be true. So constructing this argument is where the creativity comes in, right? The template for the proof is given, and then the argument is where the creativity happens. There's no set path to follow, but for basic proofs, it's often possible to just follow your nose. It's customary then to rewrite the proof, leaving all relevant details, and any attempts that turned out to be unfruitful, kind of rewriting them, leaving them out. It may not be the best of customs. It would probably be helpful to see the struggle necessary to create a given proof. But nonetheless, we're going to follow the custom of polishing up our proofs. Like a piece of music, you don't include all the various versions and missteps that you didn't like, right? You just record one final perfect version of your song. Okay, so we're going to need a theorem and a definition to prove that the sum of two integers is even. This theorem I'm just going to give you. We're not going to prove it. You can just assume that it's true. The sum of two integers is an integer. Everyone agree? And the product of two integers is an integer. Okay, good. So our definition of an even number, we're going to define an even number as an integer n is even if you can write it as 2 times k, where k is some integer. Does that sort of fit the flavor of what you think of as an even number? Like 8, right? 8 is even. The reason it's even is because you can write it as 2 times 4, right? And 12 is even because you can write it as 2 times 6. Does that make sense? So every number that's even, it's even because it fits this definition, because you can write it as 2 times something, where that something is another integer. Yeah, because it would be equivalent to say n divided by 2 gives you an integer, right? Where n equals 2k is the same thing. Divide both sides by 2. I'm sorry, multiply both sides by 2. Equivalent. But n equals 2k is a handy definition for the proof. Okay. All right, so we're going to prove theorem 2 here, that the sum of two integers is even. So we are going to assume n and m are both even, right? We assume the if part of the statement. If n and m are even, then n plus m must also be even. So we're assuming n and m are both even. We need to show n plus m is even, right? Yes, but that's not what we're proving right now. Yeah. That's actually one of your exercises to do later. All right, so if n and m are both even, we need to show n plus m is even. So this is a good way to start the proof. What do I know? What am I trying to show? All right, so now that I have that written, because n and m are both even, I can use the definition of even. So that means n can be written as 2 times a number, and m can be written as 2 times another integer. They're not necessarily the same integer, so I used k and j. With k and j elements of the integers. Okay. So if n is even, that means it can be written as 2 times an integer. M is even, it can be written as 2 times an integer. They're not necessarily the same number, so that integer might be different. So I use 2 different variables there. All right, so thus, n plus m is going to be 2k plus 2j. Pull out a 2. j plus k is itself an integer, right? So this is 2 times another integer, and that's the definition of an even number. Thus, by the definition of an even number, n plus m is even. And then put a little check, the proof is complete. Just take some practice. There's a few exercises for you to do, but you can come back to it after you do your practice with the sets, or you could do it now. But your classwork starts with making sure you know all of your table mates. And if you have any questions, put up your flag and I'll come around and help.